Welcome to Friday. It's the 11th, and it's the shells method we're doing today. Huh? What? Do what? No, I'm not restarting nothing.
It's like 1, 2, 3, go.
No, I can't do the go because then it doesn't come out. I tried that already. Anyway, so we're over here, and let's try. Oh, did I not give you 88 AB3? Here it is. All right. Whoops! I should have given that to you already. New packet for today. Okay, I'm going to focus on the shell questions first, then we can come back to other stuff if we have time. 1, 2. 1, 2. There you go. All right. So let's take a look at 88 AB3. 88 AB3. That's a B. Okay. All right. Let R be the region in the first quadrant enclosed by the hyperbola x squared minus y squared equals 9, and the x-axis and the line x equals 5. Y equals 0 is the x-axis. Find the volume when you generate this region about the x-axis and about the line x equals -1. A is disks, B is shells, all right? So let's do A just for a warm-up. Now if you graph this thing, it's one of those hyperbolas that has x-intercepts or y-intercepts, not both. Whoops. That's weird. Okay. So which does it have? Does it have x-intercepts or y-intercepts? If you plug in x equals 0, you get y-intercepts. If you plug in y equals 0, you get x-intercepts. What if y is 0? What's x? 3 or -3. There's a branch out here and there's a branch out here. So we're talking about in the first quadrant, right? Okay. So here we go. Origin, 1, 2, 3. There's the x-intercept. That's a hyperbola that goes like this, right? But we're only talking about the functional part, right? If we solve this for x in the principal root, and that curve, the x-axis, and the line x equals 5. Okay, so here's the line x equals 5. Pretend. Okay. Pretend I hit the 5 there. So this is x equals 5, and this is x squared minus y squared equals 9. Well, actually, no, it's just the functional part with the principal red. Let's get y alone. How do you get y alone? Nice of you to join us. Always a pleasure to see you coming in on time. You have any paperwork, my friend? No? Yes? Pass? Something? All right. Well, anyway, that's really not... Yeah, take one. That's really not what we're graphing. What are we graphing? Can you get y alone? Subtract x squared. How about subtract y squared, add 9, and square root it? Yeah. All right. So how about rad x squared minus 9? Good. Okay. So y equals the principal root of x squared minus 9. All right. So it's that top half of that piece. Okay. Okay, so I want the volume of revolution around the x-axis and the volume of revolution around the line x equals -1. We'll get to that. If you do, again, it's up to you. Do you want to do horizontal or vertical strips? If you do vertical strips, you get thickness in dx. I know you're most comfortable with that, apparently. And if you revolve that around the x-axis, you get a disk, right? All right, so let's just set up a disk for fun. This is not new. So the volume around the x-axis is going to be what? How do you set it up? Pi, the integral from 3 to 5 of r squared dx. Who's r? That's right, so we square that and we get x squared minus 9. And the thickness was? Dx. And this isn't too bad to integrate, is it? So what do you get? Pi times what? X cubed over 3 minus 9x evaluated from 3 to 5, look what they did to you. There's no dropping out of the 0 stuff, huh? All right, fine. Come on. So 5 cubed is what? 125? 5 times 9 is what? 45? Minus, plug in 3, that's 27 thirds minus 27. And that whole thing is times pi. And there's a lot of ways you can simplify this. Whoops. But how about if I just do the like terms for now? 125 thirds minus 27 thirds is going to be 98 thirds. negative 45 minus a negative 27 is really negative 45 plus 27 is negative 18, right? Is that right? 18 more than this is 45, yeah, okay. And if you want common denominators, you're going to multiply top and bottom by 3, which is 54 thirds from 98 thirds is 44 thirds of pi. All right, that was just a warm-up. Now, here's the new stuff. 54 from 98, yeah. Okay, don't get stuck on the easy stuff. That's arithmetic. All right. Now, consider the line x equals negative 1. Let's say it's out here. This is part B now. This is x equals negative 1. We want to take the same region that we just revolved around the x-axis. We want to now revolve it around the y-axis. Now what happens is if you take your vertical strip, it's parallel to the axis of rotation, so it's not the disk or a washer. It's infinitely thin, but then it has a circumference of rotation. All right, think of it. Think of this as like the outside of a Coke can. Right, the aluminum is very thin. Right, the outside of the Coke can. Okay. What if you unravel that? What if you unroll it? You get a rectangle. The length, there's a length and a width, or a base and a height. What's the base? The circumference of rotation. What's the height? The height of the strip. All right. So this is the height of the strip. Then we have a circumference of rotation, and then we have a little thickness. All right. So the rectangle has an area. Of base is the circumference, height is this function, and then we throw in the little thickness, then you got the volume. Okay, so we're estimating the volume of a cylindrical shell using really a prism, a rectangular box, right? Which is very, very thin, not very, very tall. All right, so how do we set this up? Well, how big is the radius of rotation? Now, this is the first time we're rotating about something that's not an x or y axis. So how far away is this strip from here? Well, this strip from here is an x value, right? If x is 4, it's 4 away. If x is 3, it's 3 away. X plus 1? Okay. Is everyone okay with that? X plus 1 away? Because, all right, so if this is 4, we're 5 away from negative 1. If this is 5, we're 6 away from negative 1. If this is 3, we're 4 away. Yeah, that's right. So the radius of rotation, x plus 1. The height is this guy, and the thickness is dx again, right? So let's set all that up. The volume of revolution about the line x equals negative 1 equals 2 pi r h dx. Okay, that's what I'm doing. 2 pi r is the circumference of rotation. Height of the strip, thickness of the strip. Okay? So what was the radius? You told me it was x plus 1. Okay, so x plus 1. What was the height? You told me. It was a given function. Rad, what the heck was it? X squared minus 9? X squared minus 9. And what's the thickness of each strip? Dx. And we're integrating from, same as before, 3 to 5. That's not changing. That's why part A is a warm-up. Okay? It says set up but do not integrate, so we're done. Yeah. Well, because remember, we have a circumference of rotation. So how do you get the circumference of a circle? 2 pi r, right? It's not pi r squared thickness. It's 2 pi r height thickness. That's a shell. Okay? All right, we got to practice that up. But that's the setup. Now, I said set it up, don't do it, so you're done. Okay? Notice how they write this. It said set up but do not integrate an integral expression in terms of a single variable. They don't want you to do something like, silly like, which is true. Isn't it the y value we're taking for the height? I mean, people do stuff like that. Some textbooks write stuff like that, and that's not considered a good thing on the AP, so that's why they're saying use a single variable. Yes, so let's use a single variable so it's easy to integrate. Now this one's not that easy to integrate because if you distribute the x, that's a u sub. If you distribute the 1, that's not a u sub. That's an advanced integration technique called trig sub we haven't done yet. So we can't finish this question yet. That's why they ask you not to do it on the AB exam, because they don't do that in the AB course, do they? All righty, so that's it for 88 AB3. Any questions? All righty. So, next. Now, if you take a look at 73 AB4, C is a washer question. Let me skip that for a minute. If you take a look at 83 AB4, take a look at the third page. We did A and B already. Haven't we seen this question like twice? Okay, let's finish it now. We couldn't do C without shells. So let's do shells for C. Okay, you ready? We're on 83 AB4. And we did A and we did B. We're starting at C. We did A like a month ago. We did B like a week ago. All right? So 83 AB4 says you have that asterisk thingy again, rad x plus rad y equals 2. Haven't we seen this 100 times already? The figure above shows the graph of that equation. Let R be the shaded region. It's not shaded, damn it. Between the curve of the x-axis from x equals 0 to x equals 1. Remember, x equals 0 is a vertical line, the y-axis. X equals 1 is a vertical line. Let's graph this out to see what the shells look like. Okay, and in part C, it says, set up a do not integrate an integral expression in terms of a single variable for the volume of the solid formed by revolving the region R by the line x equals 1. Okay, so, all right, so remember it had a y-intercept at 4, an x-intercept at 4. Looks sort of like this. And they said consider the area of the region from 0 to 1. So let's draw a vertical line at 1. Let's say it's here. Okay, roughly. X equals 1. Okay? So they're talking about this region. Now in part A we found the area. Part B we found the volume of revolution around the x-axis that was disks, right? Part C says, can you take this area, or this region, and revolve it around this vertical line, x equals 1? All right, so can you stick with vertical strips? Yeah, I think so. We did the rest of the problem in vertical strips. So it's infinitely thin. It doesn't look right, but there it is. Okay. So if we revolve this thing about the axis of rotation, notice that it's parallel to the axis of rotation. That's a dead giveaway that it's not disks and washers, okay? If anything, it's going to be shells. Otherwise, you can't set it up with our methods that we know. All right, so you tell me, what's the radius of rotation? How far away is the strip from the axis of rotation? X minus 1, because like if it's at a half, x minus 1 would be a half minus 1 is negative a half? Maybe 1 minus x would be better. What if I was at a quarter? What if the strip was at x equals a quarter? And I do 1 minus a quarter, it's 3/4 away, right? That's what you want, 1 minus x. Okay, so the radius of rotation is 1 minus x. The height of the strip is the y value. Let's get y alone. We've done this before in this question, haven't we? Okay, so that's the height, and what's the thickness of the shell? It's dx, okay? Okay. Remember, this is an estimate. We're estimating a cylindrical shell, a thin cylindrical volume with really a prism. But if we make it infinitesimally thin, the error in that estimate goes away when we add up infinitely many shells with the integral. That's what the integral does for us, right? Okay, so what is it? The volume of revolution about x equals 1 equals, what do you think?
2 pi.
2 pi times the radius of rotation, which you said was?
Oh, we need the integral.
Okay, integral from 0 to 1 times the radius of rotation?
Minus 1. 1 minus x.
Well, I think we said 1 minus x.
1 minus x.
Times the height of the shell?
4, which is the minus 4 rad x.
Well, it's not 4 though.
Plus, yeah, 4 minus 4 rad x plus x.
Here's the height right here.
Yeah.
Oh, you foiled it out. Well, you don't have to foil it out. It says set up but do not integrate. So who needs to do all that stuff? And then the thickness? Dx.
Okay, why is it 1 minus x and not x minus 1?
Well, because that gives you a negative radius, and the radius should really be an absolute. Technically, radius is an absolute value.
Oh.
So we really don't want it to be negative. In the context of these problems, positive is equivalent to absolute value. Okay. So there you go. That's it. They said set it up. Don't do it because it's a bear to do, but it's not that bad. You just you foil 3 times, and then you integrate power rule. It's not impossible. So you could do it.
So let's do it.
Well, we're going to do this one. Go to 71 AB5. All right, now, we've seen this question too. We already did part A with disks. Let's take a look at it again. All right, so we're in 71AB5. And we have, let R be the region in the first quadrant bounded by the x-axis and the curve y equals x squared minus, 2x minus x squared. Find the volume produced when R is revolved around the x-axis. We did that with disks, I think. And B, find the volume produced when you revolve this thing around the y-axis. Well, if you're using vertical strips to get disks when you revolve around the x-axis, and you use the same vertical strip when you revolve around the y-axis, that's going to be shell. All right, let's take a look at what this looks like again, remind you what the graph is. Boom. Remember, this is a parabola, right? Y equals 2x minus x squared. What kind of parabola? Smiley face or frown? Frown, okay. And what are the zeros? We've done this already. 0 and 2. Okay, good. So 0 and 2. And max is out of 1. In fact, at 1, if you plug in 1, don't you get 1? So the max is 1, by the way. But not that we really need that, but there you go. So it looks like this. If I can draw it. Ow. Okay. So this is y equals 2x minus x squared. This is the x-axis, this is the origin, this is the y-axis, and so forth. Okay. So if we do vertical strips, so there's no law against doing horizontal strips, but in this case, it's a hassle. If we do vertical strips in dx, and we revolve around the x-axis, that's got to be disk, right? But if we revolve around the y-axis, do you see the shell? It's a very thin pasta shell, or very thin outer casing of a Coke can. You know, like a Coke can without a top or a bottom? Well, there's a huge hole in the middle. It's very thin. It's just a very thin piece of aluminum going around, like a Coke can. Each strip is like a thin piece of aluminum. Then you take another strip, another thin piece of aluminum, another strip, another thin piece of aluminum, and you just stack them all on top of each other, and you get the whole volume. Okay? Is that okay? Well, what's the radius of rotation? We're rotating about the y-axis from here. Well, how far away is a strip from the axis? It's an x value, yes? Whatever x is. If it's at 1, it's 1 away. If it's at 1/2, it's 1/2 away. If it's 2, it's 2 away. It's x. Okay. What's the height of the strip? The function. What's the thickness of the shell? dx. So the volume of revolution about the y-axis is, well, how do you set it up? 2 pi, the integral from 0 to 2 of, no, we're doing dx's here. The y, it would be dy's if we had horizontal strips. And you could do it. You could do a horizontal strip and get washes out of this, but it's a bear of a problem. Hang on, we could do it. All right. So what is the radius of rotation is? X. The height is 2x minus x squared. And the thickness is dx. Therefore, you get a volume, yes? Right? 1 dimension, 2 dimension, 3. Okay. All right, so this was not too bad to do. In fact, they tell you to do it, I guess, so let's do it. How would you deal with this? Distribute first, right? So 2 pi, the integral from 0 to 2 of 2x squared minus x cubed. Okay. How's my time down there? 19, okay, that's right. Yesterday we went up to 24, and it took 14 minutes to render, so it got into the next period after our songs and everything. I don't want to mess up next period, but all right. So let's move down a little bit. So it goes over here. So 2 pi times. Now what's the antiderivative of 2x squared dx? 2x cubed over 3. And what's the antiderivative of x cubed? Minus x to the 4th over 4. And evaluated that from 0 to 2. And this one's a dropout? All right. The 0 drops out? So just plug in 2. 2 pi times. Let's see. 2 cubed is 8 times 2 is 16 thirds. Okay, minus 2 to the 4th is 16, and now we got fourths. What's the common denominator? 12. Multiply top and bottom by 4. Multiply top and bottom by 3. And you get, how many 12ths in here? 4. Well, it's 16 twelfths, right? 48 from 64 is 16, is that right? 16/12 reduces by 4 to 4/3 times 2 pi, 8/3 of pi.
Yeah, got it.
Okay, yeah, Ethan.
So you would get the same thing doing 2 pi times, like, the whole thing with 2 pi with the parallel strips, or
If you're doing horizontal strips?
then it would just be pi times the integral.
Yeah, but the thing is, then you have two functions. You know, that's an interesting question. Maybe we can do that one. Let's try it. Okay, but in this case, this is the easy way. Now, you got to be careful. Sometimes it's easier to set up the problem in vertical strips. Sometimes it's easier to set up the problem in horizontal strips. But then there's another consideration. Then the thing that you get to integrate, it might be easier to integrate if you went back to vertical strips. Or it might be easier to integrate if you went and did horizontal strips. It depends what you get to integrate. Okay, so if you expected to integrate it without a HAL, that's a consideration. All right, let me check this with HAL. Where's the heck is HAL? What was the original setup? There it is, right? So I'm going to plug this into HAL, and we better get 8 pi over 3, right? And we better get an antiderivative sort of like that. All right, so keep that up. Okay, so here's HAL. And turn HAL on. Here we go. So it's going to be 2 pi x, so 2 and pi times the integral, secant 7 of x times, remember, implicit multiply, it doesn't work here, quantity, and what was it, 2x minus x squared, right? 2x minus x squared. With respect to x, now if we just do that, we can check our antiderivative. Yeah. Well, wow. Negative 3x cubed over 6. Well,
That's the x to the fourth.
that's the x to the 4th, right, okay. 1/2, 2 over 4, 1/2, okay. And then you have a positive 8/6 of x cubed, positive 8. Yeah, Hal just combined everything as sixths instead of twelfths. Yeah. 22, okay, it's about time to put it away, but, all right. So that is the right antiderivative, but we're checking the definite integral. So comma 0, comma 2. And we get 8 pi over 3, and the decimal equivalent, if you like, is 8.378. Okay, how about we save it here? Nope, we're nowhere near done. I have not yet begun to do calculus. Hang on. Who said that? All right, so am I done yet?